I know where there's some, right here in the hall, clerk.
No, Molly, not in there. I have
Hello and welcome back to another edition of the unending editions of the 9E21 restoration. So where are we at this moment? I've got to look underneath. This is the casualty list right here. Every waxy paper cap and quite a number of carbon comp resistors have been out of tolerance and had to be replaced. Let me turn this over. But they're all done now, as far as I know. Another one could show up. This switch is loose because I needed to get in here and restuff these filter caps, which I have done. Those are done. All the waxy paper caps are done. As I said, a good number of resistors had to be replaced. What else? This guy right here, which still measures fine, had to be replaced because it'll quit just when I least want it to. So I'm finally on to the point of restoring the wire. These are the tone selectors. Cleaned those up, but this one, the green wire, had to be replaced. The cracked rubber. On this side, I'm still replacing them all of them on this side of the tone switch array are having to be replaced. They all just are cracked. And there are a couple of them inside this grounding shield right here, which is going to be a real pain to replace. But I wanted to point out one funny thing that I ran across here. Let me get you a little closer. The one funny thing is there's a coil right here, and that happens to be the tone choke. And as you can see, there's a fairly sizable choke right there, with some wire coming up through this metal ring right here and onto this connection point. And I got to looking at that and I said, well, that looks almost like a cotter pin. And I turned the radio over to look on this side, and it is indeed a cotter pin. So there's a cotter pin holding this choke in place, and the thing is, I don't know whether it should have always been a cotter pin or not. It comes right up through the case right there and has a speed nut on it. But what I do know is I'm not going to change it unless there's some performance reason to do that. I don't know what that would be, but there might be. So I've got the front cleaned up. Looks pretty good. This was what was facing up, so this side is the side that was grimy. The main chassis itself is still bright and shiny and looking pretty good. So I'm going to continue the painful business of replacing all these wires. And you're invited to watch the next episode of how this thing works. This time we'll look at tracing the FM signal path through this 9E21 chassis. So if you don't watch that, I'll see you next time. Hopefully this will be finished and we'll be ready to take some measurements and power it up. If you do watch that, hope you enjoy it. All right, let's take a look at the FM signal flow. We'll start with a reminder of what the AM side is doing. We have RF coming in here, going through a tank circuit to select the frequency that we want to look at. We amplify that RF frequency, the radio station's original frequency, induct it into or magnetically couple it, however you want to call it, into the next stage, which is the converter. At the converter, we mix the incoming RF with a local oscillator frequency, and that frequency of the local oscillator is the received, the one we're interested in, plus 455 kilohertz. That goes into the converter. They mix and match, and out comes a constant 455 intermediate frequency, so that no matter what you tune the radio to out here, you always get 455 here. The advantage is you only have to build one amplification stage, put three or 10 of them in there, I guess, but you only have to buy the components at each IF transformer. They're exactly like the one before. The tubes are exactly like the one before. You can amplify 455, 455. Finally, it comes out over here, nicely amplified, still at 455 kilohertz with our audio information on it. You put it into the detector stage, and that's where you strip out the 455, leaving nothing but the audio information. Then you amplify that one time, you capacitively couple that to the power amplifier, and you bump that way up until you get a nice high voltage here. The output transformer converts that high voltage to a high current, which drives your AM or your speaker. So you get a nice AM soundtrack. Now, one of the things about AM is it's not very high fidelity. I mean, the bandwidth on either side of the carrier frequency isn't much, so you don't get great sound. The other thing is that a lot of stuff will generate an amplitude modulated carrier frequency. When I was a boy, everything that had an electric motor, power drills, the refrigerator, the pump in the well house across the way, all made a lot of racket. They were all brush driven, and they sparked a lot, and they made a lot of noise in the AM bands. So our friend Mr. Armstrong, back in the 20s, I think it was, I'll have to refresh myself, came up with the idea of, instead of doing amplitude modulation of a carrier, let's do frequency modulation of a carrier. And that should clean up all that AM noise that we get on an AM receiver. All right, let's see how a FM, the addition of mono, and remember this is mono FM, will change this block diagram. First thing we'll add is an FM antenna. It's usually a loop of wire, a couple of loops of wire in the back of the cabinet. That's fed to the primary of a RF transformer. And the secondary, you'll notice, has a couple of lines through the transformer symbol and an arrow pointing up. That means it's an iron core coil. The secondary is a coil with a powdered iron core in it that can be moved up and down. Rather than, for example, over here, if this were a tank circuit with a primary over here you can't see, this would be the secondary, and you could tune it with this capacitor. You could change the value of the capacitor. That's the air gap capacitors that are on top of the radio, are used in the AM section. Well, you could do that just as well with a, you've got to change either the capacitance or the inductance of the coil in a tank circuit. So in this case, when they added FM to this radio, they chose to use these powdered iron core coils. And I think the reason, my guess is, I think the reason is they take up a lot less space. You have to have a lot of real estate on top of a radio to have three air gap capacitors. So they took the easier way and did it with three iron core coils. So we have this iron core coil. We're receiving FM. We've run it through this transformer. This is a tank circuit that allows us to tune which FM frequency we want to pick up with this iron core that slips inside this coil. We feed that up to the RF amp. We've, by this point, disconnected the AM input on this side. So we feed it into the RF amp. And from here on, it's kind of exactly the same with some notable exceptions. But let's run through this. Instead of an AM detector coil, we now have on the output side an FM detector coil. That goes down here. There's another iron core, powdered iron core that slides in and out to tune the FM detector coil. So we're coming out of the RF amplifier through the FM detector coil, still radio frequency, remember, our transmitted frequency with our sound embedded in the frequency changes rather than the amplitude changes. It comes up here, goes into our converter. At this point, we've added another oscillator. We've cut out the AM oscillator because we don't want to do this at 455. We'll change this intermediate frequency quite a bit. So we put in a new FM oscillator, switch it in, and now that's driving the converter. And we have the original RF signal coming in here. We have a new local oscillator signal coming in here. And out the other side, we get a new IF frequency of 10.7 megacycles or megahertz, depending on what you like. For the next three stages, all we're doing is amplifying that IF frequency just like we did in the first place. So we have, it's not the same, even though it's in a can, it might share a can with the AM IF transformer. It's a different transformer, obviously. You need a different transformer for a different frequency. But you're coupling the intermediate frequency of 10.7 megacycles to the first IF amp, do it again to the second IF amp, do it again to the detector and the first audio. And here's where we make another change, if I can figure out how. We add a limiter right here. Now, FM is not immune to AM noise, to noise caused by spark gaps like hand drills with brush motors. It's a lot less prone to picking up all that noise than AM transmitters or AM receivers, but it's not completely immune. So the cool thing with FM is you can put in a limiter stage. And what a limiter stage does is cut the top and bottom off. It clips, in essence, if you're familiar with that terminology, it clips the top and bottom of the intermediate frequency carrier, and leaving us just the frequency changes that are inside that. So we clip the top and bottom off. When you do that, you clip off any AM noise riding on the very top of the IF frequency. So you clip that off, the top and bottom. Then you feed that on into a detector and first audio. Now the detector stage does something different as well, and we'll go into that in another video. But what it does is it measures the frequency change. It picks up the audio information from the frequency change rather than from the amplitude change. So the detector for FM works differently than a detector for AM does. And it picks up, as I said, the frequency change that's being fed into it by the limiter. And again, we'll get into that in another video at another time. And that goes on out through our power amp, as usual. And by this time, at this point, all we have is audio. The audio goes into the power amp, and it's transformed and sent to our speaker. So my point of all this is it's not a different behavior, except for this and this. Picks up RF, electromagnetically couples it, amplifies the RF, again, changes it to an IF, a different IF, but it's behaving exactly the same way. It's still an IF frequency, it's just a different IF frequensee. So what have you done? You've added an FM antenna coil, you've added an FM detector coil, and you've added an FM local oscillator, all ganged together to allow you to tune the radio. You've created a new intermediate frequency, but so what? These IF amps can amplify intermediate frequencies of 10.7 megahertz just fine. You've added a limiter to clip out any lingering AM noise. You've changed the detector, the way the detector behaves. It's not a new detector, it's just changing the way it behaves so that it's looking at the frequency shift rather than the amplitude shift of the IF frequency. And finally, you've stripped away the IF and taken the pure audio and put it in the power amp. So my point is this: it's the same radio mostly. There's nothing mystical in particular about FM. There's nothing mystical or more difficult about an AM/FM radio of this age, at least, because it's fundamentally an AM radio that's been modified to accept higher FM frequencies and to behave a little differently here and there. So if you've been hesitant to crack open an AM, particularly an early AM/FM radio like this Zenith 9021 from the late 40s, there's no need to. Your body count for capacitors you can replace will about double, because there's a lot of capacitors in this radio, and your resistor count probably will double as well. But fundamentally, if you can figure out how an AM radio is working, you can figure out how an FM radio is working as well. So that's my pitch for not being nervous about FM radios. I should say one other thing about this 9021, and as I said early on in the first video, I think, this is a transitional radio. It actually has, pardon me, it actually has two FM sections. Therefore, you could consider it a 3-band radio if you wanted to. The one we just went through is the modern. There is an earlier, post-war FM frequency bandwidth. There is a pre-war bandwidth which handled a lower frequency range than the current modern FM. But the behavior is exactly the same. It's just a different frequency set, so you adjust this to pick up a slightly lower frequency range. You adjust this to do the same. You adjust this to do the same. All this remains the same because the intermediate frequency is the same no matter which pre-war or post-war, and the limiter is the same and all that. So everything to the right of right about here is exactly the same and needn't be worried about. So we've got the block diagram done. Let's take a look now at the schematic and see if we can walk quickly through the schematic and see how this is portrayed on the paper. All right, here we are. This is the most of the left side of the schematic. I got lucky and managed to find a set of schematics that showed both the switches, these guys here in both the AM and FM positions, which makes life a lot easier. But I rarely run into that, so it was a nice thing to have. Anyway, let's pick up an FM signal right off the air right here. Our loop antenna is connected to the FM antenna, fed through here and back to ground. Whatever is out there in the world is inductively coupled to the secondary of this FM antenna coil. And remember, this is the guy with the iron powdered iron core that slides up and down so that you can select a specific frequency that you're picking up from your loop antenna. So we select a specific frequency. That goes up here. Oops, through, let's get this right. Through our switch. And then up to, wandering off the beaten path there, up to the grid of our 6BA6 RF amplifier. Where it's amplified, comes off the plate, just like in the AM, goes through the primary of the FM detector transformer. It also goes through the primary of the AM transformer, which is down here, but so what? It's not doing anything. What we're interested in is the FM signal that's coming in has been amplified, selected down here, amplified by the RF amplifier, and now is presented to the secondary of the FM detector transformer. Again, a powdered iron core, movable powdered iron core transformer coil, picked up there, goes up here, and over to, come on, down through a switch, over here, and into the grid of our 6BE6 converter. This is where the converter is where the output of the, where to go? Oh, right here. The FM oscillator coil is running. Keep that in mind. So this tank circuit right here is oscillating at 10.7 megahertz plus or minus the frequency of the station we're picking up. And I don't know, it could be plus or minus, I don't know which it is. Later on, when we bring up the chassis and everything's working, we'll take a look at some of these points with the oscilloscope so we can see whether this is oscillating at above or below the received frequency. Anyway, we've got this oscillator humming along. Output goes down here, through there, back up here, over here. Kind of a laborious journey all the way up to here and down to the grid, the second grid of the converter. And out the plate right here comes our intermediate frequency carrying the audio information as FM. Goes through the first IF transformer, picked up by the secondary. Goes up to, I should try to use this key so I can draw a straight line for a change. Whichever key it is, can't remember. Not that one. Into the grid of the 6BA6 first IF. Happens again, out the plate, through the primary of the second IF FM transformer, 10.7 megahertz, through the secondary, up to the grid of the second IF, out the plate, and so on. Now let me switch this over and we'll pick up from there. All right, we've reached the third IF transformer. Couple the FM signal into there, up to the grid of the limiter, and this only gets activated when it's switched to FM to bring in the limiter into the circuit. So it goes into the grid of the limiter. The limiter, as I said, clips the FM top and bottom so that we don't get any AM noise coupled to the rest of the output. Through the plate, still IF, goes through this primary here. It gets bumped up. You can see it gets transformed upward by the discriminator IF transformer out this side and into the discriminator detector. And in here, and again, I'll save this for another video, but in here is where the FM gets detected, the slope of the FM gets detected. We'll talk about that another time. But from here on out, at the output of the discriminator, we have AM or audio frequencies only. We've stripped out the IF frequency, and that goes on out to the right to our output amplifier and speaker. So that's the path. It's no more complicated than the AM path. It does have an extra stage it goes through. It does have a different intermediate frequency oscillator, local oscillator. But that's all fine. So what? It's just a few more components to worry about. So that's how this radio works in AM and FM. I may or may not, since the pre-war FM is a unused function anymore, I may or may not take the time to figure out how to trace that through. I probably will not, since it really doesn't matter. It will be interesting once we get the radio up and running to see if there's anything going on in there. I haven't looked to see what the frequency spectrum of the pre-war FM is being used for these days. We might get something interesting. We might get a bunch of noise. Who knows? But I'll look that up for the next time we get together. So that's it for this video. Long time in the making, but a lot of other things in life come and go and get in the way of making these videos. So I apologize. And I apologize for my lines wandering all over the place. That's also the way it goes. Anyway, hope this one is okay. I'll see you next time. Be safe out there. Take care.